questions like during the talk, just feel free to unmute and ask whatever questions. Absolutely fine. But yes, I think to actually start off, I wanted to talk to sort of examine really like a baby case of how one might try and find extra structures living on Selmer schemes by just examining, what extra structures you might live on non-abelian cohomology, more than just that of a pointed set. And Netan told me it was okay for talks to go into a little bit of technicalities, so this talk will do that for the first half. So I wanted to begin with like a really very simple example where we can actually kind of quite concretely see extra interesting structures on non-abelian cohomology. And so let's start with a setup which is going to be quite familiar to anyone who's done anything with kind of quadratic Chabauty. So we'll take a profinite group G, which is basically a Galois group, but I'm just going to call it G for the time being. And let's have a continuous representation of our group G on a two-step QP unipotent group. That is, it's a QP unipotent group with a continuous action of G, and it's a G equivariant central extension of two abelian unipotent groups, so vector groups. And we'll make the additional assumption that these two outer groups, which I'm a central extension of, have no Galois invariance, and that their first Galois cohomologies are both finite dimensional. In practice, you also actually have that H2 is finite dimensional, but you don't need this in what follows. So a consequence of these two assumptions on the zeroth and first cohomology of the outer terms, these actually imply that the functor taking a QP algebra lambda to the non-abelian continuous G cohomology of the lambda points of U2, this functor is representable by a pointed affine scheme, which is denoted by H1 of G with coefficients in U2, and I'll refer to as the cohomology scheme. And by the way, throughout I'm going to be using words like continuous and topological group, but I'm not going to ever sort of bother to say exactly what the topologies are. There's some sort of inductive limit process which gives you the right topologies on these things, but I would ignore that for the purposes of understanding what's going on. So the first thing I sort of wanted to say is that, okay, this is representable by a pointed affine QP scheme, but there actually is a bit more structure on this thing than just a pointed scheme. And part of this structure you already see when you examine the proof that this thing is representable. Because the way you prove this is you use a certain long exact sequence in non-abelian cohomology, which makes this this non-abelian cohomology scheme into a torsor under this vector group over a certain subscheme of this vector group. And so you certainly have a torsor structure lying around. This is kind of relatively well known, but in fact there's more going on here than just this torsor structure on the non-abelian cohomology. So let's assume for simplicity that our co-boundary map delta over here is the zero map. This happens frequently in like local cohomology and stuff. So this means that our cohomology set scheme that we're interested in is in fact a vector space torsor over another vector space. And whenever you have an abelian group torsor over an abelian group, there's a certain construction that you can do, which gives you, in our case, an H1v2 torsor over the cube of H1u1. And the way you do this construction is you consider the H maps from the cube of H1u1 to H1u1 given by summing subsets of the coordinates. And if you pull back this torsor along this map, you end up, along these maps rather, you end up with 8 different H1v2 torsors over H1 U1 cubed. And if you take a sort of alternating tensor product of these torsors, this gives you an H1 V2 torsor over the cube of H1 U1. And then the extra structure which one finds is described very well in terms of this object, namely this torsor actually is a trivial torsor in a canonical way.
Sorry, and Alex, I'm sorry to interrupt, but I got lost a little earlier than I was expecting to. Where did that number 3 come from? I missed it.
So the number 3. So I mean, there's an analog of this construction. You can construct a similar torsor over H1 G of U1 squared, but as far as I'm aware, I can't say anything interesting about that particular torsor. It's only when you pull back to the cube of this abelian cohomology, it turns out that this thing gets a trivialization, and this is somehow to do with the fact that like single commutators do not vanish in my group U, but triple commutators do.
You're saying we haven't seen the answer to my question yet. That's what you're saying?
Yes, I'm going to shortly tell you a fact which is true
for
the value of 3, but not for the value of 2. Yes. Yeah. So what I was going to say.
Sorry.
This torsor.
Sorry about that. Oh, sorry. Does the torsor live over all of the cube of H1 U1 or the subscheme?
So I've put this assumption in that.
Oh, sorry. Yeah, I missed that. Yeah, sorry.
To make things a little bit easier to understand, I'm going to have done this. This makes this sort of rather point set approach a lot easier to describe.
Right.
Yes. So this, the theorem that I was saying is that this torsor we've constructed over the cube of H1 U1. This in fact comes with a canonical choice of trivialization. And if any of you have met the theory of cubical structures on torsors before, this trivialization is a cubical structure on this torsor.
I imagine something like this theorem is still true if that boundary map is non-zero.
I'm going to say something later, which is a generalization of this, in which the boundary map can be non-zero. I think, I'm not sure exactly what the correct notion of cubical structure is when the boundary map is allowed to be non-zero, because then rather than having a torsor over a vector space torsor over a vector space, you have a vector space torsor over some kind of other scheme, and that's less clear to me what's going on there. But I would imagine that one can say something in a similar vein to this, even if the boundary map is non-zero. Yes, and by the way, I guess maybe a sort of side remark about what cubical structures are. The reason that these things are called cubical structures in the work of Breen is that there's actually a really kind of nice example of this, a similar construction coming from algebraic geometry, because you might think that this construction here looks a little bit like something to do with the theorem of the cube on an abelian variety. And in fact, if you take a GM torsor over an abelian variety, those automatically come with cubical structures provided by the theorem of the cube. So, but that was maybe sort of an unhelpful side remark about why we call these things cubical. And so yes, I'm going to construct this trivialization for you, although you might have to take my word for it that a load of computations check out. But yeah, so this is how you construct this trivialization. A point on the total space of this torsor is represented by an 8 tuple of cocycles, which I've tried to enumerate in a vaguely sensible order, that satisfy, so these are U2 valued cocycles, and they satisfy a certain compatibility once you project them down to U1. So for example, this first cocycle should be the 0 cocycle in U1. So this is psi 0, 0, 0 should be a V2 valued cocycle. And similarly, you should have these other relationships holding in U1. And once you have such an H tuple of co-cycles, you can, if you want, check that the following alternating product, if you do it in this order, gives you a continuous V2 valued co-cycle. And so we've described a map from 8 tuples of U2 valued co-cycles satisfying these conditions to V2 valued co-cycles. And you can check rather painstakingly that this construction we've just described, in fact, gives you a morphism from this theta torsor to H1 of G and V2, and it turns out that this is giving you a trivialization of this torsor. This is the sort of the other projection of that trivial torsor. Okay, and then you also need to check it gives you a cubical structure. So there's lots of stuff to check that I'm sort of hiding, but this is this alternating product.
Sorry, for those who aren't familiar with cubical structures, could you just give a hint about what those are?
So a cubical structure is really just, it's a trivialization of a torsor constructed in, so it's a structure which exists which you can have on abelian group torsors over abelian groups, and it consists of a trivialization of the torsor constructed in this manner, living on the cube of the base, and it's required to satisfy a couple of compatibility conditions, but that they're not necessarily so interesting. Sort of quite simple ones. The fact that these things are cubical structures is going to, the description in terms of cubical structures I'm going to later soon rephrase in terms of something that's probably a little bit more familiar. In fact, I think in the next slide. So we have this is some sort of structure which is a little bit like that of an abelian group, which is living on these this H1 of U2. But there's sort of another nice way of thinking about this, because I guess, as is maybe one sort of common phenomenon, is that when you have things with cubical structures on, somehow you always have a good understanding of what sort of quadratic maps should be. And so, for example, so this allows us to make the following definition, which is, I'm just sort of picking out of the air, and we'll see a sort of a much more mature version of this later. But so the affine line A1, you can think of this as a torsor with an A1 torsor with a cubical structure over the point. So trivial torsor, trivial cubical structure. And so this allows us to identify inside we have, this is some sort of affine space as a variety, and so it has loads and loads and loads of maps to A1, but we can isolate a finite dimensional subset of quadratic maps, which are just maps which preserve this cubical structure. And like, as an example of why maybe these things are reasonable to call quadratic, if we have, suppose we have two maps from H1 with coefficients in U2 to A1, both of which factor through linear maps from the cohomology of U1 to A1. Then if I just multiply these two things together, this gives me a quadratic functional. And as I guess is maybe already apparent from the like 8-fold alternating product on the previous slide, if one is going to try and generalize this to the kind of deeper unipotent groups, maybe 3-step or 4-step unipotent groups, somehow attempting to describe something quite as intricate as a cubical structure is going to be a real pain. So in fact, it turns out, I think, to be easier to try and, rather than understanding cubical structures and all this sort of quite complicated theory, rather just to focus in on kind of maps out of the cohomology variety, because somehow we can see from this definition that on H1 of U2, we have a sensible notion really of like constant maps to A1, linear maps to A1, and quadratic maps to A1. And so what this is really indicating is that there should be some sort of filtration on the affine rings of cohomology varieties. And so if you don't know what cubical structures are, you can forget that all now, and we're just going to talk about filtrations on cohomology varieties. So here's a sort of a general construction which achieves sort of what I was doing previously, but without any assumptions of two-step unipotency or vanishing of co-boundary maps. So let's now have a representation of a pro-finite group on a finitely generated QP pro-unipotent group, or if you prefer, just QP unipotent is also fine. But you can do some things in infinite dimensions. And let's suppose that our group U is given with a filtration by subgroups, which I'm going to be denoting with W, because in my mind, I intend this to be like the weight filtration on a fundamental group. And let's put in the natural condition that one would impose on a sequence of subgroups, namely that if I take the commutator of an element in weight minus I, an element in weight minus j, that should lie in weight minus I minus j. And yeah, this is condition is satisfied for the weight filtration on fundamental groups. It's satisfied also for the descending central series filtration on fundamental groups, which are often the same. So this is quite a natural condition. And similarly to the previous case, we can if we impose some assumptions on the Galois cohomology of each of these graded pieces, which is by the way a vector space, then we get the fact that this cohomology functor is represented by a pointed affine QP scheme. So, and so then the sort of interesting extra structure that I want to sort of talk about, and which I will show later is actually relevant to non-abelian Chabauty, is the following. The affine ring of this cohomology variety, in fact, comes with a natural filtration, algebra filtration, induced by this filtration that we chose on our group U. And I'm actually going to tell you two different ways that you can construct this filtration. The first of which is actually somehow quite hands-on, and the second one's going to be a little bit more abstract. So the sort of concrete way you might want to construct a weight filtration on this cohomology variety, well, we'll go in 3 steps. First step is the affine ring of my pro-unipotent group comes with a natural filtration induced by the filtration on my group, because, well, U is isomorphic to its own Lie algebra via the logarithm isomorphism. So its affine ring is the same as the affine ring of its Lie algebra. And now the Lie algebra is just a vector space being viewed as a variety. And so its affine ring is the symmetric algebra in the dual of the Lie algebra. And now, under this logarithm isomorphism, this filtration that I chose on U is a filtration on the Lie algebra by subspaces. And so there's a corresponding filtration on the dual of the Lie algebra by subspaces, and this induces an algebra filtration on the symmetric algebra. And so this gives us a Hopf-algebra filtration on the affine ring of U. And so the next stage, once we know that the cohomology variety is representable, so cohomology scheme is representable, we also know that we have a kind of a cocycle scheme which represents the functor of cocycles. And moreover, this scheme, whatever it is, it comes with evaluation maps. If I take an element of my group G, I can take a cocycle and I can evaluate it at that element to get an element of U. And so these maps give morphisms of schemes. And so in particular, they give maps via pullback from the affine ring of U to the affine ring of this scheme here. And all I do is I take the finest algebra filtration on this affine ring, which makes all of these evaluation maps compatible with filtrations. And finally, the affine ring of the cohomology variety is a subalgebra of the affine ring of the cocycle scheme, because you have a map from the cocycle scheme to the cohomology scheme taking cocycle to its corresponding class. And so you can just take the subalgebra filtration, the induced filtration on the subalgebra from the filtration we constructed in step 2. And so this is a kind of more or less explicit description of what this induced W filtration on the affine ring of the cohomology variety is. And there's also, but this same filtration can be also characterized via a universal property, which I guess gives you a second construction. So if you are given a W filtered QP algebra, i.e. an algebra with an increasing filtration, which I'll usually be noting by W, then you define the lambda points of my filtered group U just to be the set of homomorphisms of filtered algebras from this Hopf algebra to lambda. And this thing is a topological group. And so we get then a cohomology functor going now from filtered QP algebras to pointed sets. And you can then prove via exactly the same argument that gives you representability of the usual cohomology functor that this functor is also representable by a W filtered algebra. And if you forget the filtration on this algebra, you get the affine ring of the cohomology variety. And so this effectively characterizes the weight filtration on the W filtration on the affine ring of the cohomology variety in terms of a universal property representing this functor. And maybe I should also say, sorry, Emmanuel?
Sorry, Alex. So you're saying this filtration is the same as the previous one, you're saying, right?
This is the same filtration, yes.
Right. In the previous, this must be a really dumb question, but in the previous construction, it's sort of not, is it completely obvious that it's not a trivial filtration in some sense? I mean, I can imagine a filtration with one level being the whole thing and then another level being 0 or something. And
yes, yeah. And this problem has definitely bit on us before in different contexts. But no, this one, this one definitely is not the trivial filtration because so if you do this all with an abelian U and maybe you assume that your filtration is supported in weight minus n, then what you get out of this construction, it turns out, is the
symmetric algebra filtration or something.
Exactly, the symmetric algebra filtration on the dual of H1 with coefficients.
I see. Okay, I see. Yeah, that makes. Yeah, thanks.
No worries. That's a good question. Yes, and so I was going to just briefly say that the meat of this theorem is representability by an algebra by a filtered algebra. The fact that the underlying that if you forget the filtration, you get the affine ring of this cohomology variety. This is actually some sort of formal fact. Like you chase around some sort of representability of functors and Yoneda facts, and this gives you this. But one thing that's sort of interesting about this construction is it actually allows you to get your hands a bit on this, on what this filtration actually looks like, which maybe also goes some way to answering Mignon's question. So when you do this when you follow through the argument, what you in fact prove is that this non-abelian cohomology scheme is non-canonically, it is a closed subscheme of the product of all the Galois cohomologies of its graded pieces. So these are vector space cohomologies, and I'm viewing them as schemes in the natural way. And so this means that the affine ring of this is a quotient of the affine ring of this product of a load of vector spaces, and it turns out that the filtration on this is just the one which is induced from the filtration on the affine ring of the natural filtration on the affine ring of these things. And what this means in practice is if you, this is sort of like an archetypal example, something I'll be using a bit later, if you tell me the dimensions of the Galois cohomologies of each of these graded pieces, I can produce you an upper bound on the dimension of each of the like W filtered pieces of the affine ring of the cohomology variety. So I think this is sort of what I wanted to say about the technicalities of how one constructs, where weight filtrations on the affine rings of cohomology schemes comes from. And now I want to sort of change gears a little bit and talk about what this actually means in the context of non-abelian Chabauty. And I guess my title sort of maybe betrays that this is something to do with counting the number of rational points. So to begin with, I just want to very quickly recall what's going on in non-abelian Chabauty, though undoubtedly absolutely everyone here is an expert. But so let's suppose we have an S-integral model of a hyperbolic curve. We pick a suitable prime and a suitable base point, and we also choose a suitable Galois equivariant quotient of the QP pro unipotent SR fundamental group of the geometric generic fiber. And by suitable here, I mean, well, I have a particular thing I mean, but this includes the quotients by the descending central series, quotients by the weight filtration, and also these extensions of the abelianization by QP1, which are studied in quadratic Chabauty, at least in Jenna Nettan's first papers, where they study those sorts of things. All of these are suitable quotients to do non-abelian Chabauty with. And you can then construct from this U a diagram, which sort of has the following shape, where I'm not going to define all these objects, but you have your global points map into some sort of global Selmer variety, your local points map into a local Selmer variety, and there's a comparison isomorphism between the local Selmer variety and a certain quotient of the de Rham fundamental group of the generic fiber. And there are sort of, I don't know, I sort of think there are really three key facts about this diagram, which tell you that you can do anything useful. And these facts are, firstly, that these local and global Selmer schemes are in fact schemes. They're constructed initially, I guess, as functors, and you show they're representable. And the localization map between them is an algebraic map. Secondly, this comparison isomorphism between the local Selmer scheme and this quotient of the de Rham fundamental group, this is an isomorphism of schemes. And lastly, the most difficult fact to verify, I guess, is that this map here, I've called J de Rham, the de Rham-Kummer map. This is a locally analytic map with locally Zariski dense image. And in fact, you can be really explicit about what this map is. Like, you can write down a description of coordinates on this guy in terms of differential forms on your curve Y, and then this map here is given explicitly in terms of iterated Coleman integrals. And then one of the main sort of facts about non-abelian Chabauty is that suppose that for our particular choice of U that we've made, that the dimension of the global Selmer scheme is strictly less than the dimension of the local Selmer scheme. This then implies that the set of S integral points is finite, and this sort of goes by the recipe, which is, I'm sure, now well known to most of us, or all of us really. But the point is that this dimension inequality is telling us that this localization map is non-dense, has non-Zariski dense image, and this means that there has to be a non-zero functional on this quotient of the de Rham fundamental group, which vanishes on the image of the global Selmer variety. And then if you then precompose this with this de Rham-Kummer map, this gives you a non-zero analytic map vanishing on the S integral points, and that gives you finiteness. And so where do weight filtrations fit into this picture? Well, so in this setup we were talking about, U is some kind of quotient of the fundamental group, and so naturally comes with a weight filtration, which in the case that U is, if our curve is projective, this is just the descending central series filtration. So it's nothing particularly exotic. And so by what we've talked about in the first half, this was the more sort of technicalities-based half, this means that there are induced filtrations on the affine rings of the global and local cohomology varieties. Sorry, I just saw the something flashed orange, and yes, Ellie asked a good point, and Netan's answer to that question is the correct answer. Yes, and so the your global and your local Selmer schemes are closed subschemes of these cohomology schemes, and so in particular, their affine rings are quotients of the affine rings of the cohomology schemes, and so there are natural induced W filtrations on the affine rings of global and local Selmer schemes. And then we need sort of somehow three corresponding facts to the previous three facts, which I should say this is the bit that I'm currently dealing with the write-up for, but I'm confident that these things are true when I say they're facts. The first is that we have this localization map going from the global Selmer scheme to the local Selmer scheme, and this map is we said that this map is in fact compatible with the weight filtrations on the affine rings of either side. This actually is basically formal. The second assertion is, well, the de Rham fundamental group also admits a natural weight filtration on it, and so there's a natural. This puts for us a natural weight filtration on the dual of this particular quotient of the de Rham fundamental group. And so our second assertion is that this comparison isomorphism we had between the local Selmer scheme and this quotient of the de Rham fundamental group, this isomorphism is strictly compatible with the weight filtrations. And then the final assertion is that somehow the weight filtration on the affine ring of this quotient of the de Rham fundamental group has some sort of intrinsic meaning. Namely, if I take a functional on U de Rham mod f naught, which is of weight n, then when I compose this with the de Rham-Cohen map, what I get out is a linear combination of iterated Coleman integrals of length at most n.
Alex, if you were question about number 3, if you were to replace weight filtration by descending central series filtration, would this be false?
I don't know.
I'm mostly used to working with examples where the difference, where they're the same, obviously, so I'm confused about this too.
I think somehow this should work also with the descending central series filtration. I think this is I think the numerics that I'm doing later become a little harder if you use descending central series in the place of weight filtration, but I think I would guess that it should just go through, because as is kind of apparent, all of these constructions are kind of just formal.
Okay.
Yes.
Maybe I may be a little bit confused, but for a general U,
yes,
isn't the weight filtration or refinement of the descending central series filtration?
Yes.
So this should be better somehow, right? And
well, I guess it's a refinement, which I guess means that elements which show up in like weight -2 might sort of be in the first step of the descending central series.
Right.
So,
right.
yeah, I've always found the weight filtration easier to work through the numerics with, but I don't know whether it's necessarily better or worse than the other.
Yeah, I think that's right. I mean, I think that's the way they did it in Hodge theory as well, in Haynes' papers, that weight filtration is somehow easier for a number of reasons.
Yeah. Yes. And yeah, I guess sort of maybe a little related comment, which will appear in a second. You can actually define the weight of a Coleman integral, and these are in fact give you iterated Coleman integrals of weight at most n, but in particular they have length at most n.
Sorry, maybe one other question. I don't suppose you know that localization map is strictly compatible, right?
I don't know that. No. If I did, I think I could. Actually, no, I don't. Yeah, I think if I did, I would be able to improve a couple of numerics in a couple of places, but it's sort of quite far from clear to me why that should be.
Yeah, it may not be true. Yeah, if it were, I think there would be lots of nice consequences, but
probably yes.
Maybe there's no reason.
Yes, but with these three facts, you can actually somehow slot these into exactly the same argument we did on the previous slide for non-abelian Chabauty, and you can obtain a slightly more precise statement potentially or sort of different statement of the main theorem of non-abelian Chabauty. This looks of this shape. So let's suppose that the dimension of the weight n part of the affine ring of the global Selmer variety is strictly less than the dimension of the weight n part of the affine ring of the local Selmer variety. Then we can make the following more precise statement that the S integral points of y is contained in the vanishing locus of a non-zero linear combination of iterated Coleman integrals of length at most n. So this affords us kind of control over the lengths of the Coleman integrals which cut out the set of S integral points. And I guess somehow the proof is sort of the same as the previous. Now, rather than saying inequality of dimensions implies non-density, what we say is that the localization at P map induces a map on the affine rings, and this is filtered so it induces a map on the weight n pieces, but now we have a map from a big dimensional vector space to a small dimensional vector space, and so this map has to have non-zero kernel, and the kernel of this map produces us a functional on the on this quotient of the Durand fundamental group with this weight n, and then that's what gives us the length bound on the Coleman integrals.
Sorry, Alex.
Yeah.
First of all, this is great actually, because I think you've made very precise something I got confused about for years. It is very nice.
Oh,
yeah.
Thanks.
But secondly, I don't suppose, again, this is related to the previous question, but I mean, it's conceivable to have elements inside the kernel of this dual localization map without the dimension bound, right?
Yes, absolutely.
Have you investigated that question?
No, I have not. No. That is a very interesting question, and I know you have, a few ideas of where you might find elements of these kernels of these maps. But I haven't yet succeeded in sort of doing anything interesting with that idea.
Yeah. Okay. Yeah. Thanks. No, it's great.
Yes, and the reason, by the way, that one cares about lengths of iterated Coleman integrals is that there's some machinery developed by Jen and Netan, which I not really, because I don't entirely understand how to fully apply, but I can apply in some particular cases. The point is that this machinery it allows you to bound the number of zeros of linear combinations of iterated Coleman integrals if you know the length of those Coleman integrals. And this appears in their paper on effective non-abelian Chabauty, with a sort of focus on the quadratic case. And so so the idea here, and this is something that is sort of still fleshing out the whole what shaped the whole picture should be is that weight filtrations on affine rings of Selmer schemes should give you bounds on lengths of Coleman integrals and hence bounds on the number of S integral points. And I wanted to sort of make this a little bit explicit right at the very end by looking at an example, and the example I will choose is really the example. It's sort of the first example anyone ever sees of non-abelian Chabauty. And this is, of course, the projective line minus 3 points. So let's see how this all works in this particular setup. So we'll take a finite set of primes, or I'll write little s for the number of primes in this set, just for notational convenience. And so the hyperbolic curve that we're interested in is the projective line over ZS minus these 3 points, 0, 1, and infinity. And now a sort of kind of useful observation, which will actually be familiar to anyone who is in my project group in Arizona, is that if I have an S integral point on P1 minus 3 points, and if I have a prime V inside S, then in fact, there are somehow 4 different types of S integral points. You have those S integral points which happen to be V integral, because V is an S, they don't have to be V integral. You have those which lie in the residue disk of infinity, those which lie in the residue disk of 0, and those which lie in the residue disk of 1. And so what I want to do is to use this this observation to focus in on a particular subset of the S integral points, and maybe at the end I can sort of say a little bit why this actually turns out to be a useful idea. So for each place inside S, I'm going to pick a preferred cusp, so a choice of 0, 1, or infinity, and I'm going to look at only at those S integral points which for each place in S are either V integral or they reduce to the chosen cusp. So for example, if S were 2 primes L and Q, I might say look at those S integral points which L-adically don't lie in the residue disk of 0 or infinity, and Q-adically don't lie in the residue disks of 1 or infinity. And yeah, by what I said earlier, in fact, the S integral points on Y are covered by these sets, of which there are 3 to the S. It turns out to be a lot better to bound the size of each of these sets independently and then add up at the end. And I guess I'm sort of going to sweep a lot of stuff under the carpet to do with the construction of Selmer schemes, but whenever we have a suitable quotient of the fundamental group, we can make something which we would call a sort of refined Selmer scheme corresponding to these choices of cusps, and this is a closed subscheme of the global Galois cohomology, and it contains the image of this particular subset of the S integral points under the non-abelian Cohen map. And so yes, and it turns out we can actually understand what these things are. So let's start off with a relatively simple case. So let's take the maximal 2-step unipotent quotient of the fundamental group. So this is a central extension of QP1 squared by QP2. And then using using sort of Soulé vanishing and a bit of sort of bookkeeping via Hilbert series, what one can show is that this weight filtration that we get on these Selmer schemes, well, okay, it's supported in even degrees for sort of maybe obvious reasons, and the weight 2n part, the dimension of the weight 2n part of the affine ring of the local Selmer scheme is the nth coefficient of this particular power series, while the dimension of the weight 2n part of the affine ring of the global Selmer scheme, we don't know it exactly, but we can upper bound it by the nth coefficient of this particular power series. And what you observe from this is that if if little s is at most 2, then the top power series has larger coefficients in general than the smaller one. So in particular, more precise statement, if s equals 2, then the t squared coefficient of the top power series is bigger than the t squared coefficient of the bottom power series. And so we have this inequality that I talked about, and so this will tell us that this particular subset of the s-integral points will be contained in the vanishing locus of a non-zero linear combination of multiple polylogs of weight at most 4, so length at most 2. And in fact, this assertion I made here is one which is very familiar to my project group from Arizona, because they actually explicitly worked out what this length 2 condition should be. And so I sort of wanted to give it a little sort of brief shout out to what they managed to do. So they sort of focused in on the example where S is 2 primes L and Q, and we're looking at points which are L-adically not in the residue disk of 0 or infinity, and Q-adically not in the residue disks of 1 or infinity. And then they found that what this defining equation that this theory gives you actually is in practice. It turns out it has this really nice symmetric form where you have some particular coefficients which have been computed by Ishai and Stefan, and the multiples of Li2 of Z and Li2 of 1 minus Z. So this part of the theory, I guess, has been like really explicitly worked out. But one advantage of these weight filtrations is I sort of alluded to the fact that you can do lots of Hilbert series computations, and this means that actually you can say quite a lot of things in higher depth too. So for my sort of final trick, I'm going to do something which is maybe a little unorthodox. So the particular quotient of the QP pro-unipotent fundamental group I want to take now is the whole thing, which is infinite dimensional, but nonetheless this theory all still works, because it turns out that this weight filtration on these affine rings is all of the steps of the weight filtration are still finite dimensional, and you can still work out what they are. And one nice thing about the whole QP pro-unipotent fundamental group is that you can actually this top formula is somehow especially nice. This dimension of this weight filtered piece is the nth coefficient of this particular power series. The corresponding thing for the upper bound on the dimensions of the weight filtered parts of the affine ring of the global Selmer variety are a little bit more complicated, but you can still get a good enough handle on these things to show the following, namely that basically when n equals 4 to the s, you get the expected dimension inequality. And what this tells you is that this particular subset of the s-integral points is contained in the vanishing locus of a non-zero linear combination of multiple polylogs of length at most 4 to the s. And now you can actually use this nice differential operator machinery that I alluded to earlier, developed by Jen and Netan. And what that will then tell you is it'll tell you an upper bound on the size of this set Y ZS superscript sigma, and that will in turn give you an upper bound on the number of s-integral points on P1 minus 3 points, because we have 3 to the s different choices of sigma, and we've got some bound on each of those independently of the choice of sigma. And when you kind of run this all through and use Bertram's postulates at one point, this actually tells you that you get an explicit upper bound on the number of s-integral points of P1 minus 3 points, namely 16 times 6 to the s times 2 to the 4 to the s. And on the one hand, I think this quite an interesting result, because this is, I guess, an indication that you can use non-abelian Chabauty techniques to address effectivity and uniformity questions. Because, for example, this formula here only depends on the size of S. It doesn't depend on exactly which primes you have. And what this tells you is that you get an explicit upper bound on the number of s-integral points of P1 minus 3 points, namely 16 times 6 to the s times 2 to the 4 to the s. And on the one hand, I think quite an interesting result, because this is, I guess, an indication that you can use non-abelian Chabauty techniques to address effectivity and uniformity questions. Because, for example, this formula here only depends on the size of S. It doesn't depend on exactly which primes you have. And yeah, so I think this indicates this is actually quite a fruitful idea. On the other hand, and to finish my talk on a very slight downer, the question of counting the number of S integral points solutions to the S unit equation is a thing which people have studied a lot. And people have studied this in particular using analytic techniques, and we are still a long way off being able to compete with the analysts in this competition, because they have the best known analytic bound is of exponential type, and the bound that at least I can get out of this at the moment is doubly exponential. So we're still trading the analysts in this regard. But yeah, that's what I wanted to say. Thank you. Does anyone have any questions?
Alex, one thing is presumably this method still gives you ways to find the points or not?